In this video, we are going to talk about a board which can be controlled by your smartphone, and this board is going to be used to, I don't know, for example, control relays or some other interfaces. It can be mounted inside of a car, so there is a special power requirement, and there is also security. So basically it can be controlled only by specific people from specific smartphone. Correct, Daniel?
In a nutshell, yes.
Okay, and in this video we are going to have a closer look on the schematic, on the PCB, and on the manufacturing, and also on some kind of process, how this project kept improving as you develop this board. Okay, perfect. So anyone who is into electronics, who is designing something which goes to production, can find this video interesting. So first, let's start talking about this schematic. We are going to have a closer look at the circuit. So we mentioned it's going to be controlled through smartphone. So how this is done?
So this, indeed, it's for controlling. It was designed to control locks, open doors and gates, both in buildings physically, but also for cars, through a smartphone. And then, of course, you want it to be wireless, and we've selected Bluetooth as the wireless connection method.
What kind of module do you use? Can we have a look on specification of this module?
Yeah, of course.
So if someone is interested to do this kind of device, and so this can give them idea.
Yeah, that's right. The module that we selected, at some point, it's already a few years ago that we selected this module. But back then, Vanstel, they are a manufacturer of wireless modules with Nordic chipsets. Earlier, we had already decided on a Nordic nRF52 chipset. They're very commonly used for Bluetooth connections, actually, Bluetooth Low Energy. And Vanstel offered a cost-effective option with also, and that's very common with wireless modules, they've already done pre-certification. All the required wireless measurements have already been performed with this module. So if you use this module in the way that the manufacturer has pre-certified it, this simplifies your certification of the end product quite a bit.
I would like to highlight this because I've seen some people who are designing devices, they sometimes forget about certification, especially for wireless devices. It can be also very costly. So it's not only about complications which you can have during certification, but it's going to cost a lot. So if someone is designing a board with Wi-Fi or Bluetooth, then maybe consider using this kind of modules because it can make everything easier.
Yes, it can make everything easier. And in the end, it's a commercial decision, a commercial trade-off. Because if you use a module, your end device will be more expensive per piece. But if you have to pay a lot less for certification because your certification is so much simpler and quicker, there's an optimum. So there's actually a decision you have to make early on in your design process for which quantities are you designing and which option makes most sense.
So theoretically, I'm sorry for interrupting. So theoretically, when designing for example, for hundreds of devices or maybe even like 1,000, you can go for module, and once you go to hundreds of thousands, then you can redesign the area where you have module and you can put there the chips if you like, or something like this.
Yeah, exactly.
Exactly.
That's indeed a common approach. 100,000 sounds maybe already like a lot, but where the trade-off is depends on the module price and what offers you're getting for certification.
Okay, so what is the next thing in the schematic? And I would like to point out you have permission to show this schematic. You have permission to show the PCBs, because or before I should mention, like, you are a freelancer, so you design these kind of boards for clients, and your client gave you the permission to share the schematic and PCB because they are software company and basically they know how in the software, so they are not really worried about people knowing about the hardware, correct?
Exactly. I'm a freelance electronic engineer. I'm sort of work as a one-man design bureau. It's not only the electronics. I try to be the full thing. So basically, designing the whole product, on even guiding to series production. And this company, my client for this product is indeed a software company. They're security specialists, so they don't really have the knowledge on how to make a physical product. So that's why they hired me. And indeed, their unique their unique sauce, their unique know-how is in the software part and the authentication algorithms. That's their real specialty. And the electronic design of this product is relatively simple and straightforward. There's nothing unique and patentable in this design. So indeed, that's why they gave me permission.
Okay, and that's why we are showing this, because if someone would like to design this kind of boards, there are many boards which are basically very similar, Bluetooth or wireless controlled I/O board. That's basically what is this.
Exactly.
So okay, we have the module. So what kind of interfaces, or what do you switch on, switch off? Oh, I guess, yeah, it's on the second page, interfaces.
That's right.
Yeah.
So that's an Altium sub schematic.
Mm-hmm.
So like I mentioned in the beginning, this device was made to be as universal as possible. So for as many different kinds of doors and gates and locks and even for cars. So it has also a kind of general purpose I/O pins. So these four over here, they can switch either to the input voltage VBAT or to ground. So each output can switch in both directions. Those are just universal, either positive or negative outputs. It also has two additional outputs that can only switch to ground. And it has a specific interface here that's called Wiegand. And Wiegand is also it's a really old keypad interface. Now I remember it. So it's even from the time from punch cards, where you had a punch card to open the door. So it's an input interface which only passes a binary code. This is also to interface with specific kinds of doors with this existing Wiegand interface when it's already if it's an old electrical door. And there's also oh no, wait, sorry, it's not in this version. This version is only outputs.
Okay.
There was also a version with inputs at some point, but we don't have them anymore.
Okay, and then there are some protections, I see.
That's correct. Yeah. So we have here, those are Zener diodes. What they do, the way I've placed them here, because you need ESD protection, and I also want an overvoltage protection if there is any voltage coming from the output pin, which can happen if you're switching an inductive load, like a relay or a coil. And when you switch off the coil, the voltage from this coil can actually jump up. So you want to be able to protect your MOSFETs from this excessive voltage, and that's what these Zener diodes do. So they are rated at 33 volts. That's well within the maximum of the MOSFETs. And if the voltage on this pin becomes higher than 30, then a bit above 33 volts, then they start conducting and they absorb this voltage peak.
And then I see there is a polyfuse, or what is it?
Sorry?
Polyfuse F1.
Yeah, as well. Actually, other thing I wanted to mention about the Zener diodes is that the nice thing is that in reverse direction, they start conducting at their Zener voltage. But in their forward direction, they start conducting at the normal diode voltage of 0.7 volts, for
okay.
example. So they actually also protect for negative voltages at the same time.
Mm-hmm.
And this polyfuse here, indeed this little structure that you see here, is a small input over voltage,
Mm-hmm.
over current, and reverse voltage protection, all in one with two components. It's a really simple trick. So what you have here, this is actually also a Zener diode, Transorb, which is just a BV Zener diode. This one starts conducting a little bit above 30 volts. So its holding voltage is rating is 30 volts. So below 30, it will definitely not conduct.
Mm-hmm.
Once you come a little bit above 30, it will start conducting. So if your input voltage becomes higher than 30 volts, this guy starts conducting. At some point, the current that starts flowing is larger than the rating of the polyfuse. And what the polyfuse does, it's a resettable fuse. So once you cross its trip rating, then it disconnects the input. So that's how it's protecting your circuit. And it does that by heating up.
Mm-hmm.
So as long as it's hot, it stays open. If you remove the over voltage, then it will start cooling down, and at some point it will connect your circuit again, and it will continue working as normal.
Mm-hmm. Basically, for anyone who never used this kind of fuse, it's basically like standard fuse, but you can use it multiple times. You don't have to change it after once it blows up. Or
Exactly. And that's the convenience about it. They are more expensive than one-time use fuses. Disadvantage is that with a one-time fuse, this one is soldered on the board. So if that one would blow, we'd have to throw away the whole board. And because this device is made for very custom installations, I mean, you have generic inputs and outputs, it's very easy to make a mistake while installing this module.
mm-hmm.
So to make sure that the installer doesn't have to throw away the module if he makes a little mistake, that's why we chose for this option.
Mm-hmm. Okay.
And also, even if we zoom out a bit, it's a service-mounted device. So even though per piece this fuse is a bit more expensive, we don't have to pay for a fuse holder. We have a very simple automatic pick-and-place production. And simple production is cheap. So actually, it's saving money in production. So the difference between the normal fuse and this one in the end would not be very big.
Okay. Now, I think what many people may ask about is how do you come up with what kind of rating you have to use, for example, for this protection diode? Because I've seen so many times people like, oh, I can use this super small resistor for, I don't know, 60 watts or something. And I'm like, oh, you have to be more careful. Like,
Yeah, exactly. Yeah, you really have to check all your ratings, especially also for the components that are your protection, that are protecting you within these ratings. So this device was designed for a battery voltage range of 5 to 30 volts, with a peak input rating of 36 volts. So we want to have normal operation until 30 volts. If you have a little peak on this input voltage on 36 volts, no bad thing should happen. So that's what this input protection was designed for. So it has a hold voltage of 30 volts. So until 30, all is good. Now, slightly above 30, around 33, 34 volts, it will start conducting. But the Zener voltage, the diodes, they have a curve of current voltage that goes up exponentially. So around 33, 34 volts, you got a few milliamps of current flowing. But once you go to 35, 36 volts, that's where this voltage starts increasing. So in the end, what you have to take into account is what's the maximum voltage that you will get on this Zener diode before it starts conducting enough current to blow the polyfuse. And that combination, that's what you need to design the rest of your circuit for. So for this circuit, I actually don't know the number by heart. But this polyfuse also has a curve. The more current you run through it, the faster it blows. For example, this is a 750 milliamps polyfuse. So at 750 milliamps, it can work indefinitely. At 1 amp, it will start heating up. I believe at 1 point something amps, it will slowly blow, and at 2 amps, it will blow almost instantly. So also with the peak voltage ratings of all the devices that are connected to this voltage line, VBAT, you have to design them for this voltage. So these MOSFETs, for example, they need to have a voltage rating that's sufficiently high to survive this peak in input voltage before the polyfuse blows.
But theoretically, so this is mostly designed for automotive, correct? So theoretically, it
One
would
of
be
the use
like
cases.
usually 12, or what is the other one? 24 volts? I don't know.
That's right.
So theoretically, there should not be, if there is something about 30 volts, then it would be only some kind of peak because, I don't know, you start your car or something. I have no idea when this peak will happen.
Exactly.
So it should not be like continuous 34 volts, or unless maybe they connected the other way around or something, and then there.
No, yeah, indeed. And actually, this design, it was so if you look at the ratings for normal operation of the bus voltage in a vehicle, for cars, it's normally 12 volts, but during normal operation, this can easily go to 15 volts. For a truck, that's a nominal rating of 24 volts, but during normal driving, it can actually easily reach 30 volts. So this design, it was actually only designed for cars and vans, not for trucks, because this continuous 30 volts would already be at the edge of what this design can handle. So that would actually be too marginal already.
Okay, so what kind of power supply you have on this board?
Yeah, well, good question. Because we have a wide input voltage range, especially also a pretty high one compared to the internal voltage, because our Nordic processor runs at, what is it, 2.5 volts I designed it for. This voltage difference between 30 maximum, 2.5 internal.
You
Well,
can't use LDO.
exactly. So that's why I use a switching converter. That's what we have here. Pretty straightforward Texas Instruments switching converter.
Do we have datasheet for this one? Just have a look.
Yeah. Let's move here. Yeah, there we go. So it's
150
I selected
milliamps.
this
That's not
device.
big one, 150 milliamps.
No, that's right. So very short summary of how you select this device then. Well, you look at the ratings that you have. Those are your requirements. So we have an input voltage rating that we determined earlier with a continuous input voltage and peak absolute maximum voltage. So those are two criteria that you select for. And you add up all the users of the output voltage on your PCB. Well, in case of this design, I'll come back to the design in a little bit. The only users that we have are the Nordic system on chip. And this chip over here, this is a secure element, basically like a SIM card. And two LEDs over here. Well, if you add the current consumption of those devices together, it's almost nothing. We are around 50 milliamps maximum. So, well, it's still, of course, smart to select a power supply chip with a higher rating to have some margin for error, but 150 milliamps is almost the smallest I could find.
So you only have like one power supply on whole board?
Well, let me check.
Because what is the power for the Nordic chip? Is it?
So the power for the Nordic chip comes indeed from this power supply.
What is the value?
But there's something a little bit funny going on here. So we have the output voltage from the DC-DC converter here. But then we have this diode here and this capacitor. And this capacitor is a supercapacitor. We added this device. It was a request from the client, the software company. because for their algorithm to keep it responsive when you disconnect power for a short time, it helps their algorithm if the device can keep its time it keeps its internal clock running for some time if you disconnect power. So that's why I selected the supercapacitor, because it's a relatively cheap way to keep the Nordic chip running for a few hours.
Oh, that's nice.
Yeah, so that's why we have this structure, because when you remove the input power, this whole part of the circuit will be unpowered.
Yes.
And we don't want the supercapacitor to drain to
Yes.
the power supply. So that's why we have a diode in between. And the maximum voltage rating of this supercapacitor is 2.5 volts. So that's why the whole digital circuit is now 2.5.
And the module can run from 2.5 volt?
Yeah, the Nordic NR52 chipset, from the top of my mind, can go from 1.5 to 3.3 volts. So then we have a nice margin between the 2.5 volts that we charge the supercapacitor to, all the way down to 1.5, or whatever the number is. But that's the minimum for the Nordic chip. So that gives us a nice discharge, the total charge that it can run on.
And then how do you control the transistor? Can we go back? Because there's like very low voltage. So
Yeah.
I think, yeah.
Yeah,
Oh,
so that's,
there is one more transistor before the transistors.
yeah, that's right. So indeed, the important thing is that these low side transistors, so those are the MOSFETs that are switching ground, they should have a gate voltage rating that's sufficiently low that they can still be switched by the Nordic at these low voltages.
Yeah.
So your gate threshold voltage needs to be low enough. It's maybe important to mention that when the Nordic is in backup mode, so when its voltage is lower than 2.5 volts, we don't need to switch the outputs because there's no input voltage anyway.
But still,
So
2.5 volt is quite low.
Oh yes, yeah.
And because you have there the supercap, it can go even lower.
Yeah, but that's the point. When it's getting going
Oh,
lower,
it means it's not powered on. Ah, okay, you are right.
exactly. So we don't need to switch anything. So
So
we only
okay.
need to consider.
So, but I wanted to point out, if someone is designing this kind of circuit where they are using transistors, they have to double check also what is the gate voltage. If the gate voltage is enough to fully open or fully control or properly control the transistors or MOSFETs.
Exactly, yeah. Even if you have a relatively simple and straightforward design as this, you still have to take into account all the ratings of your components.
Yeah, okay. So what else is on the schematic about? The secure element. Can we have a look on the secure element?
Yeah, sure. There's this guy over here.
So you say this is like SIM card or?
Yeah, that's right. This is basically the same kind of chip as what you would have internally in a SIM card.
And what does it do? So you somehow send some kind of request like.
Well, to be honest, I'm not fully sure what it does because this is part of the algorithm,
the software company,
the software of my client, which I didn't design.
Okay.
They only told me we need this secure element because that's what our system needs.
And you connect it through SPI bus, and I guess basically it probably works something like this is my key, and tell me if the key is correct or not, or something like that, I guess.
It will be something in that area indeed. Yeah.
And when the authentication is okay, then it means you can control the outputs.
Yeah, it's this is pre-programmed for the devices by my client. So on the one hand, with this secure element, they can verify that the device that they are connecting to is actually one of their devices that has been integrated into their systems. It authenticates the device, but it can also use it with the algorithm that's running on the Nordic processor and the keys that are stored in here. It can also authenticate a user. So even when the user is offline, he does not need to have an internet connection, but only with communication between this device and smartphone of the user. They can both authenticate each other, and both can be certain that they're talking to the person who says that they're talking to.
Okay, so there is a transistor in power line. Yeah.
That's right. A P MOSFET.
So why did you use it?
So in this low power backup situation, where we only want to keep the clock alive in the Nordic, we want to reduce the power consumption of the board as much as we can.
So
we
you
want to switch
disconnect it.
off everything that we don't use. And indeed, at that moment, we turn off the wireless communication, we turn off the LEDs, and we don't need a secure element at that moment. So with this MOSFET in the power line, we can actually physically switch off the power to the secure element. There is something that you have to take into account when you do that, because not only the power will be removed from the secure element, you also need to make sure that your I/O pins are also at 0 voltage or floating. So that's why this little notice here, because if you remove the power from this chip, but you still have an I/O pin, for example, the chip select at high, then this whole chip will actually be powered through this I/O pin.
Yeah, I know
That's why you
this.
get an I/O leakage.
Because there are, I mentioned this multiple times in my videos. Very often people forget what is inside of the chips. One of the components inside of the chip is ESD protection diode. And if the voltage on pin is higher than the power voltage, then the voltage from the pin will flow to the power of the chip.
Exactly.
Yeah. Okay. So now we can have a look on PCB, I think.
All right.
And before we continue, I would like to point out you have also improved version of this board, or a little bit different version of this board, which is the second one, and then we will little bit later we will talk also about the second version.
Exactly.
Okay, so it's 2-layer PCB or no?
Exactly. Yeah. So we are still designing with manufacturing series production in mind. So while electronically it's not a very complex thing, we are designing for a commercial product, so it needs to be cost effective. So we need to lower production costs where we can. So two decisions that you can see here in this design. Well, the first one is that it's a 2-layer PCB, indeed, only a top layer and a bottom layer. And secondly, all the components are on the top side. So if you look at 3D, all the SMD components are on the top side. So it only needs one production pass through the pick and place machine and with flow soldering. And there is only one through hole component. Ideally, if you look at production costs, normally you want, for series production, you want to have as much SMD as you can instead of through hole. Because SMD is always an automated production process that's very cost effective with a pick and place machine. But if you do through hole at lower quantities, that means that actually someone has to manually grab this part and put it in the PCB. So that's more expensive.
I would like to again point out this because there are many people who never seen how PCB is made, how the boards are assembled. I highly recommend to watch these kind of videos. I have done some videos, so I will put link somewhere, and everyone can watch it. It's very important to know how these boards are manufactured because then they can help to design better boards. And exactly what you explain, one of the many things what to think about, how much assembly is going to cost. And if we can place all the components on one side only, that can make production much cheaper. Because some people, they ask me, I've done some tutorials. And in one of the tutorials is a keyboard tutorial, and I place all the components on the top. And some people ask me, like, but maybe we could place the decoupling capacitors directly under the microcontroller. And yeah, we can, but then it has to go through the assembly line twice. It costs more money. And exactly as you said, for through-hole components, basically they have to physically take these boards, move it to different working place. There are people who will have boxes with the components which they need. They have to put the components inside of the boards, and it has to go through the, I don't know, for example, wave soldering, or I think you mentioned you also use the selective soldering, or how is it called?
Yeah,
We will
selective
talk
soldering.
about this a little bit later. So it's like additional process, more money for production.
Yeah, indeed. Like Robert says, look at how it normally works. And also, in case of doubt or in your design, you have something specific that you're not entirely certain about how that would be produced or how that could be done efficiently, don't hesitate to talk to manufacturers, because in the end, they also want to sell their service. So they're more than happy to discuss with you what an efficient design would look like.
Yeah. Okay. So was there something tricky on this PCB layout?
Mm, Not very much, actually.
Because I would be really worried about two-layer PCBs. I remember I only designed a couple of two-layer PCBs. Almost all of them, they had problems. So now I don't really design two-layer PCBs. I rather do four-layer.
Okay. Well, maybe one thing that's good to mention, that you mentioned it, because with RF boards, where you have radio on board, your grounding is very important. And actually, now that you mention it, I did do a little trick with the grounding here, because the layout is relatively simple. There's no high-speed traces, no very high currents or whatever. But what I did put effort in is making sure that I got as much as possible a solid ground layer. Because this ground plane that helps me meet my EMI requirements, and it keeps the performance of the antenna on this module optimal. So for both of these, you want to have as solid ground layer as you can. So what I did in this design is that I tried to route as much of my signals and power lines on the top layer. So that's what you see here, all the digital traces, all the power lines, they are all flowing around on the top layer. On the bottom, I have connecting lines where I need them, but I keep them as short as I can, and I make sure that all around it, I have sufficiently thick ground traces, with also lots of ground vias around it, to make sure that electrically this board is as much as possible one solid ground layer.
Okay, so why did you design second version? What were the improvements, or what did you learn from this design?
Okay, well, this design was already from quite a few years ago, and there indeed, like we said earlier, we focused on as many different applications as we can. But we noticed on the commercial side, when we started selling it, that we were actually selling most of them for use in cars and vans. That's apparently where there was the biggest demand in this product. But this device had a big disadvantage for use in a car, because the outputs, they have a rating of 200 milliamps each. And in the automotive world, 200 milliamps is nothing. That's enough to switch a relay, but nothing more than that. So if an installation company wanted to install this in a van to unlock the doors, well, then you normally have the back doors to the storage area and the front doors where the drivers are. So you have multiple doors that you want to open and close, which also means that you need to control multiple relays, which then do the actual switching of the voltage to the lock motors. So in the end, we had a very cost-effective small device that we could sell to the client, to the customer. But then he had to spend quite a lot of money in installing and wiring all these relays. So commercially, it turned out that that's where the most demand was, but our device was not really optimal for that market. So that's why we decided to go for a new design version, which was the in-car edition, which was specifically made only for installation in cars, vans, and trucks.
So the control circuit, I guess, is very similar.
Exactly. I'll show you the schematic first, actually. Because if you look at it, you will recognize almost all of it. It's essentially, the digital part is essentially the same circuit.
There is one more power supply now, I think.
Very good. Yeah, because there's one difference. In the previous one, we designed it for cars and vans with a bus voltage of 12 volts. Already mentioned for trucks, our input voltage rating was a bit too low. Now we also want to go for trucks. So we have increased the input voltage rating from 30 volt maximum to 36 volt maximum. Now with a 40 volt peak rating. But then we have a bit of an issue because we want to have the relays, instead of all these external relays, we want to have them in the device to make it simpler and therefore cheaper to install for the end customer. And we also would prefer to have one device version because looking at the size of the markets for vans and for trucks, it was not the commercially most interesting option to have two different devices. We just want to have one that we can sell to the whole automotive market. But that means automotive relays, they either come with a 12 volt coil or with a 24 volt coil. And
so you needed a 12 volt output, and then maybe from 12 to the 2.5, or what do you use?
Yeah, essentially, indeed, we need an intermediate voltage. We first need to go down from the maximum of 36 down to somewhere around 12, so that we can use one type of relay. But then we still need to go down to the 2.5 volts for the digital circuit. So in the end, what I came up with is that we still have our switching power supply at the input. A different one, by the way, because it was a few years later. So now there was a new device that turned out to be the best option with all the requirements that we had for this design. With an output voltage, unusual output voltage of 9 volts. Reason for that is that 9 volts is the minimum voltage at which the automotive relays can still switch at all operating temperatures. And why do I want to go to the lowest voltage? Well, because then the difference between this intermediate voltage and the 2.5 volts for a digital circuit is as small as I can get it. And if it's pretty small, well, the current consumption on digital circuit is still very low. So that actually allows me to use an LDO. And LDO is not only simpler, but also cheaper and smaller. And those are all advantages that were very useful for this design.
Okay, I understand now. Okay, so we've seen this. So go back to the other schematic page. I would like to see how the relays. Yeah, how the relay.
Yeah, here you go.
Oh, so there is the protection diode for relays.
Yeah, indeed.
Yeah, that's what I mean. Yeah.
It's actually the same point as here's the same relay, but it's flipped. But don't let that distract you. It's often called a freewheeling diode, and indeed, like we talked about earlier, you're switching an inductive load. So if you turn off your MOSFET, you will get a kickback voltage, which will be higher than your switching voltage. So to protect your MOSFET, you place a diode.
Okay, is there anything other special about this?
Yeah, maybe one thing that's nice to mention. You see here this this is Dutch external fuse. Because we are in an automotive environment and we are going to switch very large currents. We are directly switching the lock motors now, so they need to be protected with a big automotive fuse. And in the first prototype design of this same board, there was actually a big automotive fuse on this board. And then we went to our customers with this prototype, and they already liked it a lot because it was way easier to install than the first version. But they were saying, yeah, very nice that you place this automotive fuse in your box, in your device, but I need to run a 12 volt wire from the car battery to your device. And this wire also needs to be protected. So I have to place a fuse at the battery where I'm taking this 12 volts. So the extra fuse that you have in your device, it's actually a bit useless. You need an external fuse anyway. So that's where, discussed with my client how we would do this. And we decided to remove it, this automotive fuse from the PCB. And instead, they are delivering with this device, they're delivering one of those wire-mounted automotive fuses, fuse holders with fuse, so that the installer has everything he needs to install the correct fuse. But with the strict note, you need to install this at the point where you take your 12 volts. And this also allowed us to make the device a bit smaller again.
Because I've seen the fuse was very, very big in the. If you go back to the previous project and when you open PCB, I think that's on the left. No, yeah, it looks big.
Yeah, but that's the polyfuse actually. That's not the automotive fuse.
Ah, okay.
So the automotive fuse,
It was even bigger.
it would be well, from here till here, basically. It's huge. Maybe you know it from in your car when you have to replace a fuse in the fuse box. 50 amps fuse is compared to the rest of
Oh,
this piece.
it was like standard car fuse?
Yeah, the
Ah,
standard
okay.
automotive fuse. So don't be fooled because we are pretty far zoomed in right now. But if you look at the real size of this PCB, then this automotive fuse is already very big. And the same goes for this design, because if you look at this one in 3D, this is the same polyfuse, by the way, this green block. So you can imagine that with the big automotive fuse in here, that's actually quite.
Oh, so you kept the polyfuse there, but they also need to add the extra fuse to protect the wires.
Yes, very good point actually. Because we need the automotive fuse to protect everything that goes to the door lock motors. But that's a 15 amps fuse. If anything goes wrong on the digital part for whatever reason, that's never going to blow this 15 amps fuse. So if you install the input voltage in reverse, for example, well, you don't want to blow your 15 amps fuse if they accidentally wire the plus and minus wrong.
Yeah.
So we still have the polyfuse with the same input protection circuit. So with this over voltage protecting Transwarp. So the same trick again, but now with a much lower rated polyfuse, so that only this guy triggers if you install the plus and minus wrong.
Okay, so now I think we can move to maybe production. So it means you need to do some kind of testings after this is built, assembled. So how do you support testing on this board?
Yeah.
Because I think, again, many people, they forget. They design circuit, they design PCB, and they completely forget about what is going to happen after the board is built. I even seen boards without JTAG or without possibility to flash the chips, and people were like, oh, okay, I forgot.
Yeah, you even already need that during your development and debugging, but during production you also need it. Yeah, that's indeed, and that's actually a much bigger point than a beginning electronic designer might maybe think. But building one PCB is a very different game from building 1,000 PCBs. And you really need to think about an efficient way to test all of them, because from those 1,000, there will be 5 or 10 PCBs that have a production mistake, that have some reason why they don't work. So you need to be able to pick out those 5 or 10 pieces. Because if you send them out to your customers and they have to come back to you saying, hey, I got a broken device, that's bad marketing and costs for warranty. So yes, that's a very important thing. So what we did with actually the first board that I earlier showed, it's relatively low quantities. If you go to really high quantities in production lines, they often make a bed of nails setup where you have poco pins that connect to test points on the PCB. And then they have some kind of automated test equipment that runs a test script to test all the functionality that you need to test.
I've done a number of videos on this topic. Again, I will put the video somewhere.
Excellent. Very interesting to see as well. Also, complete field of engineering on its own. But for a few hundred boards, too expensive. So for this previous one, I made a very simple 3D printed, I tested it with a few poker pins that was able to show if the inputs and outputs were working with LEDs. And the flashing the microcontroller, putting the software on there, is done with, in both versions, with this connector over here.
Mm-hmm.
So this is called Tech Connect. It's
Can we find it? Can we find
for
it?
you. Sorry?
Can we find the example of these pogo pins or this connector or on internet? Because maybe again, not everyone may know what does it mean, pogo pins or.
Good point. This is just a commercial product. It's not the only one.
Yeah.
There are competitors. But this is one that I happen to have and like.
Mm-hmm.
So it's basically a manual
You can click
bit of
there,
apps,
yeah.
sort of.
Make it
You got
bigger.
these 6 pins.
Click there. You can
and
make it
that's-
bigger. Click there.
Yeah.
Yeah.
So you got
perfect.
these 6 pins, and you can connect this header then to your programmer and debugger. So during development, you can use it to debug and test your software. And because it's a SWD interface, you even get a terminal. So your print statements, you can also read out through this same interface. And then in production, you can use that same connection to flash every board.
Mm-hmm. You have to hold it down by hand, or how do you hold it?
Well, now we're talking specifically about this product. They actually have a little clip that you can place
Oh
on
yeah,
your
I see it there on these other pictures down. Yeah, there are some
Oh,
clips.
yeah, there it is. Yeah, so there's a little clip that holds it in place. Well, if you can get some nice sponsoring from Tech Connect for this, it's actually a very convenient product, and that's really how you can hold it in place when you are debugging.
So this one goes from the other side?
Yeah, that's right.
Mm-hmm.
Yeah, like this. So that's just what you use during debugging, and then.
But it means you need to keep space around this on the bottom.
Yeah, that's right. And good news, there is. That's actually why I placed it at the edge of the routed area. Because actually there shouldn't be components here, because this is the antenna area of the module. But nobody says that there can't be a clip before a debug connector.
But it's interesting, you have the points from top and also from the bottom?
Yeah, that was actually reason for that is that during development, this is actually where this clippy comes in. During development, it's convenient to push in the connector from the top side, place the clippy on the back, because here there's space for the clip. Then my client can do their software development and debugging. But during production, this board was designed for larger quantities. This one is designed for thousands of units.
So for bed of nails, it's better to have all the test points on the bottom.
Exactly. If at some point, we don't have it right now actually, but in the future, if we want to go for a bed of nails, in this way, we already have our bed of nails connections for the flashing of the microcontroller. And because I made this, as you can see, it's very much squeezed in, the whole design, to make it as small as I could. So the most logical place for the other, the second set of programming connectors was directly opposite of the top one.
Okay, so now we skipped to testing, but I forgot to talk a little bit about the production, because I mentioned we would like to also talk maybe about the soldering these through-hole pins which you have there. So what was the problem there, or what do you have to keep in mind when you are using these through-hole components?
Exactly. Well, like we talked about earlier, through-hole is what you rather not do, because it's a, especially at lower quantities, it's a very manual production process, and manual is expensive. But for these connectors, these are very commonly used in the automotive world. And for these relays, they are only available in through-hole versions. So here, I mean, we are talking about currents of 15 amps. So we have no other choice but to go for through-hole. But still we want to keep the production cost as low as we can. So we still have all the SMD on one part of the board, on the top layer. So we still have only one pass through the SMD production chain. And now the through-hole components are placed in such a way that they can then be placed as a second production step. So after the SMD is placed and soldered, the through-hole components can be placed in the PCB. For these pin connectors, there is actually, we don't do it right now, but if you go to higher quantities, it is possible to use a sort of assembly jig that makes it easier to either manually place all these connectors on the right place in the PCB, or even at some point have a robotic arm doing it. But then we're talking about really high quantities. And then on the other side, that's where the pins have to be soldered. Now, as you mentioned, Robert, there are two ways you can do this. You can either use wave soldering, which is as cool as it sounds. I can definitely recommend to watch a video on that. But for wave soldering, that will either cover the complete bottom part of the PCB, or you have to shield certain sections off. And that's what I designed this PCB for shielding sections off. So the wave of liquid tin will hit the bottom side of the PCB, apart from the masked off protected areas. And you need a certain spacing around it. So the distance between this pin and this hole was designed such that it's enough so that we can place a mask on top of this hole and the pins over here.
What kind of mask they do? How they do it? Because originally I thought they just put their tape, but I think you told me they don't really put the tape. Something different has to be used.
I haven't seen maybe for lower quantities they do tape actually, although I haven't seen it at the manufacturers. What I have seen, but that's for products that go in really high quantities, so thousands of 10,000s of boards. Then they actually make custom masks. So each PCB or PCB panel is placed in a holder. And that holder has a sort of shield on the bottom that covers certain part of the bottom side of the PCB, so that when the wave of tin hits the bottom side, it doesn't hit that part of
I understand.
Yeah. And then there's also a second option that's actually more common for lower quantity or medium quantity boards. That's selective soldering, which actually also is really very cool to watch. Definitely watch a video on it, where you have a very thin fountain of tin that selectively only solders the pins that needs to be soldered with sort of robotic arm. There you also need to keep a distance between where your tin fountain is and where the components are that shouldn't be soldered. So again, this is our critical distance between this pin and this hole over here, and that's a sufficient margin that they can use basically any normal selective soldering nozzle. Now then you might be thinking, hey, but there are two through holes here.
No, I'm more thinking about the other through-hole components, but I guess through-hole components can be close to each other, yeah? Correct?
Oh, yeah, that's right. Because they
can just move the fountain around or something.
Yeah, the nozzle can drag itself from pin to pin, or it can certainly go doop, doop, doop to each pin that it needs to solder. But that doesn't matter. As long as of course, there is a minimum spacing that you need to keep, but that's for any kind of through-hole soldering to prevent bridging between the solder pads. But a distance like this is no problem at all. You will not get bridging with this distance.
Okay. Anything else about assembly or testing we forgot to talk about? Was there something special?
Yeah, maybe the reason why this hole is here. So what you can see through this hole is an LED. This is a through board LED. Why did we use the through board LED? Well, because we wanted the LED we also had in the previous board. We wanted it to shine on the front side of the device, on the top. And how this board is placed in the housing is that this is the front side of the device, because the LED should be pretty close to the plastic of the housing, because if it's too far away, then you don't see the LED. But we don't want any components placed on the other SMD components on the other side of the PCB, because that would mean a complete extra SMD production cycle only for one component. So the cheaper alternative was to take a through board LED. It's a little bit more expensive than a normal LED, but it's just a normal LED that's mounted upside down and shines through the PCB.
Yeah.
And there we spend a bit more on the component itself, but we save in assembly.
Yeah, I use this on keyboard.
Oh, sweet. Nice.
Yeah, because on keyboard usually you have the switches from the top, and the switches they should lie on the PCB. And if you would like to have LED under the switch, then it's one of the options is just place it under and make hole.
Yeah, exactly. It gives you, as a designer, it gives you an option for optimization.
Yeah, but from production, I think until I assembled maybe third board, first 2 times they always ask like, oh, this LED is mounted upside down, or it doesn't fit on the footprint, or yeah, it doesn't fit on the footprint because basically number 1 is on the side which is not, when you rotate it and you have the LED facing top, you can't rotate pin 1 on the LED on the pin 1 on the footprint. You have to flip the LED and then pin 1 will be correctly placed. So they kept asking me like, how do we place this LED? It's upside down.
Well, they see it when they open the tape in the tape and reel, right? They see that they are upside down. So I did have a very fancy pick and place that can juggle the LEDs.
I don't know how they are on the tape actually, because I think the LEDs which I use, they can be mounted in both directions, I think.
Did you not ask your manufacturer, Robert, how he does this?
No.
This one that I have here is actually upside down in the tape and reel, because then he can use the normal pick and place to pick it, go to the right location PCB and place it there.
Maybe they are upside down in the tape. I should check the datasheet. I don't know. I never saw about this.
Yeah.
Okay.
No, that's a good thing. Yeah.
Okay, now
that's one of those things.
No, go ahead. Go ahead. What do you wanted to say?
Oh, sorry. That's one of those things where you come up with a design option. Then you need to check if what you've designed is indeed also the best for your manufacturer. Is this something that's easy to assemble for him? Because, for example, if it is an LED that can be placed in both directions, but it's in the tape the right side up, then that would mean that they have to flip it during placement. And you can't do that with an automatic pick and place machine. So then they actually have to place it manually.
Or they have to repack the reel.
Or repack, yeah. Which are both, they add costs. So it's a trade-off.
You're right.
One.
I should check it. You're right.
Yeah, but I can imagine if it's made for reverse mounting, then they probably place it upside down in the tape.
Okay. Now what is missing is the enclosure. We didn't talk about the enclosure. So what do we do about the enclosure?
Well, that's a very good point, of course, because now I've shown you the electronic design, but the PCB is not a complete product that the end customer gets. So that's again where your work as an engineer moves to a different field. So this was for the first board that we talked about. That was at the hundreds of units. For those quantities, your only option is an off-the-shelf housing.
So existing housing?
Exactly. So this is a housing that you can buy. The type is actually in the name here. It's from Hammond, if I'm not mistaken. That you can just buy at any distributor. And then what you can do is also what many PCB production and assembly companies can do, is that they can modify this box. So
make the openings.
Yeah, exactly. And of course, the less modifications you have, the better. So in this case, the modifications I made are this hole here for the connector, this little hole here for the LEDs, and this hole for the reset button. And then we got a housing for our product. And this is, well, if you then look at what that costs, so you have the cost of your off-the-shelf housing, then you have the cost of your modification. So, and then you end up between 5 or 10 euros per product.
Mm-hmm.
If you have quantities up until a few hundred, maybe up until 1,000, then that's just the most cost-effective option that you can do.
Mm-hmm.
But if you got,
Theoretically, I think you could do also 3D printing, but I'm not sure how reliable the 3D printing is for automotive. I don't know.
yeah, in that case, you'd have to use a bit more advanced 3D printing with different materials. But for prototypes, definitely,
Yeah, prototypes are
even for
perfectly
this board.
fine. I'm just not sure about like long-term products.
Yeah, but you can do 3D printing with ABS or ASA, for example. Those are also relatively common for the 3D printing now, and those are automotive plastics.
But it will not be
So,
$5 or €5. But it depends how big it is. They charge based on the volume.
exactly. So 3D printing, that's if you have really low quantities, like a first trial production series, which is a really good thing to do, by the way, before you scale up to real production. Do a pre-production, and with that, go to your end customers and see if they like it or if they have remarks.
Well, actually,
That's
I do a lot of 3D printing, so and I'm like super happy how it looks. And also, some of them are really strong, and it's not so expensive. Like small parts are cheaper than $1. Bigger parts, maybe I don't know, $5 or something like this. But as I said, everyone should test number of different materials because there are big differences between materials. For example, if housing is very large, some materials they can bend or they have to test. But it's not expensive, and for prototypes, it's like super cool. For mass production, I don't know. I think it would be more expensive. So, what is the other option for mass production?
Once you go to real mass production, to real high numbers, then this 5 to 10 euros per device is actually quite a lot. But there's a much cheaper option then with a higher investment cost, and that's injection molding. Most of you have probably heard about it, but this is just how any plastic product is manufactured at high quantities. The mold, where the plastic is injected in, that's where the high cost is. That's where the big investment is, and that can really cost thousands of euros. That's why you don't do something like that for low quantities. But once you are certain about your design, you know that you're going to manufacture a large quantity of it. That's where it becomes a very attractive option because your unit cost, so how much each plastic piece will cost, goes way down. Then you can end up in the order of €1 or even less for a piece of plastic.
But I guess you have to order, I don't know, 1,000 pieces.
Yeah, you have a minimum order quantity. That's one thing indeed. But the biggest thing is the investment in the mold. Because the mold for injection molded is made from tooling steel that's milled to very exact shape. It's a pretty complex mechanism sometimes as well, depending on how complex your plastic part is. So all these things can drive up the cost. Sometimes molds can cost tens of thousands of euros if you have very complex shape in your piece of plastic. So that's, for example, the shape that you see here. This is the housing for the second PCB. I actually designed the shape in such a way that it was as simple to injection mold as possible. So these two pieces, they even use a non-moving mold. It has a different name actually in jargon, I forgot the name. But it's a mold without any moving pieces. So it's just a mold that opens and closes. And it's actually a whole field on itself, designing plastic parts for injection molding. But that's, for example, why these holes are here underneath the clips. If you have a hole here, you can have a pin that pin from the bottom half of the mold that sticks out through the plastic piece till here. Because if I wouldn't have this hole here, I would need a moving mechanism that moves a bit of metal underneath that clip. So those are the kinds of optimizations that you then also have in the plastic design to make your production cost effective.
So there are some kind of rules. This is again area where maybe people would like to see how it is done to be able to actually design enclosure properly.
Yeah, I can
Because
briefly
I heard
illustrate.
also the edges needs to be like maybe under some kind of angle so you can easily remove it from the mold, or I don't know.
Yeah, no, you're completely right. The mold has to be releasing. So when a mold consists of two halves, top and the bottom half, and in between is where your plastic is injected. And when this mold opens, you don't want the plastic part to get stuck in there. So indeed, the surfaces where it separates need to be at an angle where the distance increases sort of when it opens. So that's why all the sides, as you can see here, they are at a slight angle. They're at an angle of, oh, that's really only a few degrees, 2.5 degrees, for example. And that gives you this releasing behavior. And that's also why you have a change in direction here, for example, because this one is releasing in the upwards direction, while the surfaces here in between the connector, they are bent in the other direction. So they are part of the other mold half. Things like that, especially for injection molding, you really need to discuss with your manufacturer if your design is producible, but more importantly, what you need to change to make it easily manufacturable. So for this design that you see here, it's not only the third iteration. The first two were 3D printing, by the way. So you start with 3D printing, testing if it fits and everything. But there was also many iterations in between that I sent to the supplier where they had remarks like, hey, this might give you this issue, so design it in another way. And here you have this margin that's too small, so maybe you should change it in some way. That's with injection molding, you need a lot more communication with your manufacturer than with normal PCB design.
If someone is interested, because I know people who are watching my videos, they are not very interested in 3D, but if they are interested, leave comments, because it could be interesting to make video of factory tour video from a factory which is doing this kind of stuff, plastic enclosures.
Yeah, it's a very different field of expertise, but one that is actually something that you will definitely encounter as an electronic engineer.
Okay, what about certification? Are we going to talk also a little bit about certification? Because we have schematic, we have PCB, we talk about testing, assembly, enclosure. Only what left is certification.
Yeah, so indeed, when you have finished your design, or actually preferably when you are in the prototype phase, you also need to make sure that you meet all the rules and regulations. And that means certification testing. Now, this product was made for the European market, so that means that we have to comply with all the CE regulations. Now, interesting thing about CE is that many people call it the CE certification. But the funny thing about CE is that it's not really a certification. It's a promise from the manufacturer that you comply with all the rules and requirements from CE.
It's
But to be able,
self-certification.
self-certification sort of, but to be able to claim that, to be able to say that you meet all these requirements, you do have to do a number of tests on your device, and which test depends on what kind of product it is. In the case of a product with power connections and wireless, for example, you would need to do RF measurements, EMI and EMC, so electromagnetic interference and compliance. So if you do not emit too much radio waves at certain frequencies, but also if your device can handle emissions from other devices, if it doesn't start malfunctioning, you need to pass ESD tests. So they will actually zap your device and see if it still functions afterwards. And then depending on what kind of products you are, it's also a very big topic of complete expertise on what kind of tests you need to do for which kind of product in which situations. For certain automotive applications, you would actually need to do additional tests. Now again, because that was quite a chapter, my client decided to not go for the most complicated process, but still stay with this wireless module to at least make the wireless testing simpler.
Mm-hmm.
So even though we are now at quantities where we could switch to placing the Nordic chip on this PCB itself and then doing our own RF design, with the time that we had at that moment, and also with the cost of Verility certification, we decided to stick with the design that we had with the module for a still relatively, because it's still expensive and still takes a lot of time, but for a relatively cheap certification.
Mm-hmm. I would point out basically what you are talking about is because when someone goes to a house where they do this kind of certifications, you can just do the measurements, or you can do measurements with certificate. And the measurements with certificates are much more expensive. So for this self-certification, what we were talking about, many companies, they just go for the measurements, and that's like enough to be confident that the product is correctly designed and is working properly, and it's not really necessary to have the certificate to make the self-certification, correct?
Yeah, almost. So this testing without certificate, that's usually called a pre-compliance.
Yeah.
That's also done not in the official calibrated test lab, but in a simpler test environment with cheaper equipment that's not calibrated. And that's indeed a very good thing to do during development, because it's very fast and cheap, and it just gives you the answer. Are we probably going to pass the real measurements? So for example, if during this pre-compliance they measure, hey, we see around 150 megahertz emissions peak, that's risky. So maybe you want to check your design if you can make this emissions peak a bit lower. Now, for example, you will see that somewhere in your power supply you are generating this 150 megahertz. With a simple change, you make sure that you emit a bit less power. That's how you reduce the risk. But even for self-certification, you can only self-certificate if you have done these measurements in an official calibrated lab. So even when you write your own documentation, which you are completely allowed to write your own documentation to where you explain how you meet all the CE requirements, for certain products, again, this depends on the kind of product and the market, but for certain products, you still have certain requirements that your tests also need to meet. And often this means calibrated lab with notified body. So the real official test report from expensive lab.
Okay. And I would like to add, we didn't mention, for example, maybe like vibration testings or something like this, because for the cars.
Very good point. I didn't do it for this device because we didn't consider it a risk. And as far as I know, there was also not a regulatory requirement to do that. But if you design for automotive or for other applications where you have strong vibrations, for example, for small satellites, then designing for vibration testing is also something that you need to take into account. And then, for example, these heavy components, they become risk factors.
Yeah. Okay, I think we talked about everything. Or did we forget something? No, maybe not. So I would like to say to everyone who is still watching, if they find this kind of video interesting, where we talk about different kind of projects, maybe we could make more videos on this topic. This is basically the first one or what we ever made on this kind of topic. So if it's interesting, leave comments, because I would like to know if to continue in this kind of topics, talking about projects of different people. Thank you very much, Daniel. I think what we didn't mention, I would like you to talk a little bit more about yourself, because you mentioned you are freelancer, but you have website, correct?
Yeah, that's right. So I'm a freelancer. I basically work as a one-man design bureau, and as you've noticed by now, with quite a few areas of expertise, I try to cover all aspects, going from the first prototype, first ideas, first proof of concept, all the way to the actual end product that is being mass manufactured. And I do this for quite different companies. So some of them are, for example, these software companies or a startup that doesn't have this expertise in-house of moving from an idea to mass manufacturing. But by now also for larger companies, international companies. And there I'm more helping them with a specific expertise, for example, where they lack the knowledge in-house.
So you can do the schematic, PCB layout, enclosure design, help with testing, certification, all this.
Yeah, for certification, I assist them with going through an external certification.
Yeah, of course, you will
directly.
not do the certification by yourself, but
Yeah.
they still need someone who can help them to accomplish the certification.
Exactly. But indeed, my basis is electronic design, PCB design, and with that, pretty quickly comes embedded software. And I like to do other fields as well. So I've added mechanical design and housings over time. I've done some optical design in the last few years for quite some different applications, actually. I've designed for small Internet of Things, low power applications, but also for very big industrial equipment, for small satellites. I've designed electronics. Yeah. It's quite broad, and that's what I like doing. Experiencing all these completely different applications with the different ways of working, with the different issues that they face, the different challenges that need to be solved or improved. And that makes it very interesting.
Where are you located?
I'm in Rijswijk in the Netherlands. That's next to
Netherlands.
Delft. Delft has a technical university. That's also, of course, where I came from.
Okay, so if someone need your help, then they can contact you. You have contact on your website, correct?
dbee.eu, and feel free to contact me if I have time for new clients available, of course, because that's actually been the biggest issue the past years.
Yeah, you can pick up the best projects, the most interesting ones.
That's the luxury position, exactly.
Okay, thank you so much, Daniel, for sharing all this information, and I hope people will find it useful. Thank you.
Thank you as well.
And that's everything. Thank you very much for watching this video. By the way, we are preparing some very interesting tutorials, so if you don't want to miss them, hit the subscribe button. If you want, you can also check out our Fedevel online courses, where you will find everything important from basic board design up to advanced hardware design and PCB layout. The link is in the description. That's all for this video. Thank you again. Don't forget to leave your comments and see you next time. Bye.